We exist inside a swirling disk of 400 billion stars. The Milky Way stretches 100,000 light-years from edge to edge. That sounds massive, right? What we can see of the universe beyond it spans 93 billion light-years across, and scientists believe the actual universe might be infinite. We will journey from our galactic home to structures so vast, they make our galaxy vanish like a grain of sand on an endless beach. If you enjoy this journey through cosmic scale, hit that like button and subscribe. Let us begin. Picture yourself standing in a field at midnight, staring up at the river of light cutting across the sky. That band of stars is the Milky Way, our home galaxy, seen from inside. You are looking at the edge of a disk spinning through the void, and everything you see with your eyes belongs to this single structure. The Milky Way measures roughly 100,000 light-years from one edge to the other. To cross it at light speed would take 100,000 years of continuous travel. Scientists have confirmed this measurement by tracking variable stars called Cepheids, whose brightness pulses in predictable patterns. Each pulse tells us exactly how far away they sit. Our galaxy contains between 100 billion and 400 billion stars. Each one is a nuclear furnace, many with their own planets. Most of these stars cluster in a flat disk, only about 1,000 light-years thick at the arms. At the center sits a bulge roughly 10,000 light-years wide, packed with ancient red stars and dominated by a supermassive black hole weighing 4 million times what our star weighs. We live about 27,000 light-years from that center, on the inner edge of the Orion Arm. From our position, we cannot see the galaxy's true shape. Dust and gas block our view. Astronomers piece together the structure by mapping hydrogen clouds with radio telescopes and tracking how stars move. The rotation patterns revealed spiral arms wrapping around the core, and later observations proved a bar of stars cuts through the center. We live in a barred spiral galaxy, but the visible disk is not everything. Recent simulations reveal that dark matter surrounds the Milky Way in a massive halo extending nearly 2 million light-years outward. This invisible material creates the gravitational skeleton holding our galaxy together. Without it, the outer stars would spin off into the darkness. We cannot see this halo because dark matter does not emit light, yet its gravity shapes everything. Think of our galaxy as an island in a dark ocean. 100,000 light-years of stars and gas, wrapped in an invisible sphere 20 times wider. That island seems enormous, until you realize the ocean stretches in every direction for distances that make our home look like a floating speck. Right now, dozens of smaller galaxies orbit the Milky Way like moths circling a flame. The largest, the Large Magellanic Cloud, measures 32,000 light-years across. Most are dwarf galaxies barely 500 light-years wide. They will eventually be torn apart and consumed by our galaxy's gravity. This has happened before and will happen again. But if the Milky Way is just one island, how many others float in that ocean? The answer changes everything we thought we understood about our place in existence. The observable universe measures 93 billion light-years in diameter. Let that number settle. Not 93,000, not 93 million. 93 billion light-years from one edge to the other, with Earth roughly at the center of what we can see. This creates a comparison that shatters intuition. The Milky Way spans 100,000 light-years. The observable universe spans 93 billion light-years. Divide those numbers, and you get 930,000. The observable universe is nearly 1 million times wider than our galaxy. If the Milky Way were the size of a quarter, the observable universe would stretch farther than from Earth to the Moon, then back, then to the Moon again. Here is where it gets stranger. Scientists confirm that light travels at exactly 186,000 miles per second. Nothing moves faster. The universe began expanding 13.8 billion years ago, in what we call the Big Bang. Logic suggests that light could only have traveled 13.8 billion light-years in any direction, making the universe about 27 billion light-years across. But that logic ignores one critical fact. Space itself expands. While light travels through space toward us, the space behind it stretches. pushing the source farther away. Objects that emitted light 13.8 billion years ago have now moved to positions roughly 46 billion light-years distant. Multiply by 2 to account for all directions, and you get 93 billion light-years. This is confirmed through measurements of the cosmic microwave background radiation and redshift calculations from distant galaxies. Consider this visualization. If you could shrink Earth to the size of a virus and keep that scale consistent, the observable universe would be roughly the size of our entire solar system. A virus compared to the distance from here to beyond Pluto. That represents the scale gap between our world and everything we can detect. Every second, the observable universe grows. Light from more distant regions finally reaches us after traveling for billions of years. The edge of what we can see expands by 3 light seconds per second. That is 560,000 miles every tick of the clock. We are watching the cosmos unfold in real time, but we will never catch up to its true size. And the observable universe is merely what light has had time to reach us from. The actual universe extends beyond that horizon, perhaps infinitely. Every calculation we make, every measurement we confirm, points to one conclusion. We can see only a tiny fraction of what exists. The Milky Way is vast beyond normal comprehension. But compared to the cosmos around it, our galaxy disappears like a single cell in an ocean. And that ocean contains structures even more staggering than the space between them. 1 light-year equals 5.8 trillion miles. That single unit of measurement, 5.8 trillion miles, represents the distance. Light travels in 365 days of continuous motion at 186,000 miles per second. To cross just 1 light-year would take a modern spacecraft roughly 70,000 years. Light from our closest neighboring star, Proxima Centauri, takes 4.2 years to reach Earth. When you look at that star through a telescope, you see it as it appeared 4.2 years ago. The light hitting your eye left that star before you started reading this sentence. Astronomers call this looking back in time, and it is confirmed by every observation we make of distant objects. The Milky Way is 100,000 light-years across. Light leaving one edge would not reach the opposite edge until after 100,000 years of travel. If humans on opposite sides of the galaxy tried to have a conversation, each message would arrive 50,000 years after being sent. Empires would rise and fall between question and answer. Now, scale that up. The nearest large galaxy to us, Andromeda, sits 2.5 million light-years away. The light we see from Andromeda left that galaxy before humans walked upright on Earth. We observe ancient history when we look at the night sky, and the farther we look, the deeper into the past we peer. The Virgo cluster of galaxies lies 54 million light-years distant. Light from those galaxies began its journey before the asteroid struck Earth and ended the dinosaurs. The most distant, confirmed galaxies sit over 13 billion light-years away. Their light started traveling toward us when the universe was barely 700 million years old, less than 5% of its current age. This creates a strange reality. Astronomers do not study the universe as it is now. They study a universe that existed billions of years ago. The farther away an object sits, the younger it appears. The edge of the observable universe shows us the cosmos as it looked 13.8 billion years ago, shortly after the Big Bang. What those regions look like today, we will never know. The light showing their current state will not reach us for billions more years. But here is the cruel twist. Space expands faster than light can travel at extreme distances. Galaxies beyond a certain point are moving away from us faster than light can close the gap. Their light will never reach us. They exist beyond a cosmic horizon we cannot cross, no matter how long we wait or how advanced our telescopes become. Every photon that reaches Earth has traveled unimaginable distances through expanding space to get here. Light connects us to the universe, but it also reveals how isolated we truly are. The Milky Way sits in an ocean of space so vast that most galaxies will forever remain invisible. Yet, in that ocean, confirmed by decades of observation, 2 trillion galaxies shine, and most of them are hiding from our view right now. The observable universe ends at 46 billion light-years in every direction. This is not a physical wall. No barrier marks the edge. Instead, it is a horizon created by the fundamental laws of physics, confirmed through cosmological calculations and observations of the cosmic microwave background. Light can only travel so far in a universe that is 13.8 billion years old. Combined with the expansion of space, there is a maximum distance from which light has had time to reach us. Beyond that distance, galaxies exist, but their light has not yet arrived. Those galaxies lie outside our observable universe, and they might as well exist in another reality. Here is what makes this limit cruel. The universe is expanding, and that expansion is accelerating. Dark energy, a mysterious force confirmed through observations of distant supernovae, pushes space apart faster and faster. This acceleration means that galaxies near the edge of our observable universe are receding from us at speeds approaching the speed of light. Some have already crossed the threshold where their recession velocity exceeds light speed. When a galaxy crosses that threshold, strange things happen. The light it emits can still theoretically reach us, but it gets stretched by expanding space. The wavelengths grow longer and longer, shifting from visible light to infrared, then to radio waves, then to wavelengths so long our instruments cannot detect them. The galaxy fades from view, not because it stops shining, but because space itself transforms its light into invisibility. Scientists have calculated a future visibility limit at roughly 62 billion light-years. Galaxies beyond this distance will never enter our observable universe at any point in the future. The light they emit today will never reach Earth because space between us and them expands too fast. We are surrounded by an ocean of galaxies we can never see, separated from us not by physical distance alone, but by the very fabric of space growing between us. This creates an isolation more profound than simple distance. Roughly 90% of galaxies in the observable universe today will eventually fade from view. As space continues expanding, they will redshift into darkness. Future civilizations, if any exist, will look up at a sky containing only the galaxies in their local group. They will see a universe that appears small, quiet, and nearly empty. We live in a unique window of cosmic time when the universe is old enough to have formed complex structures, yet young enough that we can still observe distant galaxies. In another 100 billion years, most evidence of the Big Bang will have stretched beyond detection. Future astronomers might conclude they live in a static, lonely cosmos containing only a handful of nearby galaxies. But the true size of the universe extends beyond even this observable limit. Most estimates suggest the entire universe could be at least 250 times larger than what we can see. Some theories push that number far higher. One calculation places the full universe at 10 trillion times the size of the observable region. And that assumes the universe has an edge at all. Many cosmologists believe space continues infinitely in all directions, meaning the universe has no size, no center, no boundary. We simply exist in one region of an endless expanse. The Milky Way sits inside an observable bubble 93 billion light-years wide, but that bubble might represent less than 3% of reality. Everything else remains forever beyond our reach. The observable universe contains at least 2 trillion galaxies. This number comes from decades of observations, primarily using the Hubble Space Telescope, combined with mathematical models that account for galaxies too faint or distant to detect directly. Researchers confirmed this estimate in 2016 after analyzing deep space images and converting them into three-dimensional maps of galaxy distribution. 2 trillion represents a tenfold increase from previous estimates of 200 billion galaxies. The difference comes from improved detection of small, faint galaxies that earlier surveys missed. Most galaxies in the universe are not giants like the Milky Way. They are dwarf galaxies, containing only millions or billions of stars instead of hundreds of billions. These smaller galaxies dominated the early universe and merged over time to form larger structures. But even 2 trillion is likely an underestimate. The calculation only accounts for galaxies we can theoretically observe with current or near-future technology. Approximately 90% of galaxies in the observable universe remain too faint and distant for our telescopes to detect. They exist beyond our instruments' reach, invisible until we develop more powerful tools. The James Webb Space Telescope is beginning to reveal some of these hidden galaxies, but most will remain invisible for generations. Each galaxy contains an average of 100 million stars. Some dwarf galaxies hold fewer than 1,000 stars. Giant elliptical galaxies can contain over 100 trillion stars. Multiplying these ranges across 2 trillion galaxies produces a staggering estimate. The observable universe likely contains around 700 sextillion stars. That number, 7 followed by 23 zeros, exceeds the total grains of sand on every beach and desert on Earth. And those are just the stars we can theoretically count. Around each star, planets may orbit. Recent surveys suggest most stars host at least one planet. If even a fraction of those 2 trillion galaxies contain 100 billion stars each, and most stars have planets, the number of worlds in the universe becomes almost meaningless. It drowns in its own scale. The distribution of these galaxies is not random. They cluster together in groups, which gather into clusters, which form superclusters, which arrange themselves along vast filaments separated by enormous voids. The cosmic web, as astronomers call it, shows galaxies strung like lights on threads stretching across hundreds of millions of light years. Between the threads, immense bubbles of nearly empty space span distances larger than the Milky Way many thousands of times over. This structure confirms what computer simulations predicted. Dark matter creates the framework, its gravity pulling normal matter into dense nodes connected by filaments. Galaxies form where dark matter accumulates. The voids exist because dark matter is sparse there, giving gravity less material to work with. But here is the troubling reality. We can see 2 trillion galaxies now. As the universe expands and galaxies accelerate away from us, more and more will cross the cosmic horizon and vanish. In the deep future, observers in the Milky Way will look out and see only the few dozen galaxies in our local gravitationally bound group. Everything else will have redshifted into invisibility. The universe teems with galaxies, each one a separate island containing billions or trillions of stars, and the Milky Way is merely one of 2 trillion such islands, most of which remain hidden in the darkness. But knowing other galaxies exist is different from understanding how they relate to us. Our galaxy does not float alone. It belongs to structures within structures, each one larger and stranger than the last. The Milky Way you see in the night sky is a lie. Well, not exactly a lie, but an incomplete picture. The visible disk of stars and gas represents only a fraction of the galaxy's true extent. Surrounding everything we can observe sits an enormous halo of dark matter, reaching outward nearly 2 million light-years from the galactic center. Dark matter does not emit light. It does not absorb light. It does not interact with electromagnetic radiation in any way we can currently detect. Scientists know it exists because of its gravitational effects, which are undeniable and confirmed through multiple independent observations. Stars at the outer edges of galaxies rotate faster than they should if only visible matter existed. Something invisible must be adding mass and gravity. Computer simulations reveal that dark matter halos around galaxies like ours should extend far beyond the visible disk. Recent studies confirmed this by tracking the motion of satellite galaxies orbiting the Milky Way. These dwarf galaxies move in ways that only make sense if a massive dark matter halo pulls on them. By measuring their velocities and trajectories, astronomers calculated the halo's size, approximately 1.9 million light-years in diameter. This halo contains more mass than all the stars, gas, and dust in the visible galaxy combined. Estimates suggest dark matter makes up roughly 85% of the Milky Way's total mass. The stars and planets, everything we can see and touch, amount to less than 15% of the galaxy's gravitational presence. We live inside a massive invisible structure, like insects crawling through the skeleton of a beast we cannot perceive. The dark matter halo is not uniform. It concentrates more densely near the center and thins out toward the edges. Even at its edge, nearly 1 million light-years from the galactic core, The halo's gravity influences nearby dwarf galaxies. Some of these small galaxies are being slowly torn apart by tidal forces, their stars stripped away and absorbed into the Milky Way's outer regions. This process has happened many times before. Astronomers have discovered streams of stars flowing through space around our galaxy, the remnants of dwarf galaxies destroyed billions of years ago. These stellar streams trace the paths the doomed galaxies took as they spiraled inward. The Milky Way grew larger by consuming smaller neighbors, and the dark matter halo helped trap them. If the visible Milky Way is 100,000 light-years across, and the dark matter halo extends to nearly 2 million light-years, that makes our galaxy 20 times wider than it appears. Suddenly, the Milky Way is not just one island in the cosmic ocean. It is a massive, invisible mountain with a small peak of light at its summit. This revelation changes how we think about galactic size. When astronomers measure galaxy diameters, they typically measure visible light. But the true gravitational influence of a galaxy extends far beyond what telescopes can see. Most large galaxies likely have dark matter halos similar in proportion to ours, making them all much larger than their luminous disks suggest. Yet even with this extended halo, the Milky Way remains tiny compared to the next structure up the hierarchy. Our galaxy belongs to a group, and that group clusters with other groups, forming something far more immense. To understand scale, we need to zoom out and see what our galactic island connects to. Andromeda sits 2.5 million light-years away, close enough that you can see it with your naked eyes on a dark night. That faint smudge of light in the constellation Andromeda represents the most distant object visible without a telescope. But what you see is not a star or a cloud. You are looking at a galaxy containing over 1 trillion stars, and every photon reaching your eye has traveled for 2.5 million years to get there. Andromeda is larger than the Milky Way. Measurements confirm its visible disk spans roughly 220,000 light-years from edge to edge, more than double our galaxy's diameter. It contains nearly twice as many stars as the Milky Way, and its mass likely exceeds ours by a similar factor. Andromeda is the dominant galaxy in our local neighborhood, and we orbit around a common center of gravity with it. The galaxy's structure resembles ours in some ways. It is a spiral galaxy with a central bulge and arms wrapping around the core. A supermassive black hole sits at its heart, weighing 140 million times what our star weighs. But Andromeda shows signs of violence in its past. Astronomers have detected unusual patterns in its stellar disk, evidence that it consumed several smaller galaxies within the last few billion years. Andromeda is not staying still. It rushes toward the Milky Way at roughly 250,000 miles per hour. In about 4 billion years, confirmed through measurements of its motion, the two galaxies will collide. This will not be a gentle merger. The collision will take hundreds of millions of years, with both galaxies passing through each other, their gravity pulling stars into long tidal tails. Eventually, the two will merge into a single giant elliptical galaxy. Individual stars rarely collide during galactic mergers because space between stars is so vast. But the gravitational chaos will fling some stars out into intergalactic space while pulling others toward the new galactic center. Our solar system might end up farther from the core than we are now, or it could be ejected entirely. Simulations suggest we have a small chance of being thrown out of the merged galaxy altogether, left to drift alone through the cosmic void. By the time the merger completes, neither the Milky Way nor Andromeda will exist as separate entities. A new galaxy, sometimes called Milkomeda, will take their place. It will be larger, more massive, and filled with new stars formed from gas clouds compressed during the collision. This is how galaxies grow, by consuming smaller neighbors and merging with equals. But Andromeda and the Milky Way are not alone. They belong to a collection of roughly 50 galaxies, all bound together by gravity, all orbiting around their common center of mass. This structure, confirmed through extensive observations, forms what astronomers call the local group. The local group spans approximately 10 million light-years across. The Milky Way and Andromeda dominate, with the Triangulum galaxy coming in third. The remaining members are dwarf galaxies, most containing fewer than 1 billion stars. These small galaxies orbit the two giants like moons around planets, trapped by gravity and slowly being pulled toward eventual collisions. Every galaxy in the local group shares a common fate. Gravity binds them together, and while the universe expands, carrying distant galaxies away, the local group remains intact. The space between its members does not expand because their mutual gravity is stronger than the force of cosmic expansion. We are locked together, and in the deep future, we will merge into a single massive galaxy surrounded by darkness. But the local group itself is not alone. It belongs to a much larger structure, one that makes even Andromeda look small. 50 galaxies orbit through a volume of space roughly 10 million light-years across. This is the local group, confirmed through decades of careful observation and distance measurements. Every galaxy within this boundary is gravitationally bound to the others, forming a stable system that resists the expansion of the universe. The Milky Way anchors one end of the local group. Andromeda anchors the other. Between them lies the Triangulum galaxy, the third largest member, spanning roughly 60,000 light-years and containing perhaps 40 billion stars. These three spiral galaxies dominate the group's mass, but they are outnumbered by smaller companions. At least 47 dwarf galaxies orbit within the local group. Most are satellites of either the Milky Way or Andromeda. The large and small Magellanic Clouds orbit our galaxy, visible from the southern hemisphere as fuzzy patches of light. They are being slowly torn apart by tidal forces, their gas and stars stretched into streams that feed the Milky Way. Andromeda has even more satellites. Over a dozen known dwarf galaxies circle it, and astronomers suspect many more remain undiscovered. These tiny galaxies are incredibly difficult to detect because they contain few stars and emit little light. Only advanced surveys with sensitive instruments can spot them against the background glow of distant galaxies. The local group did not form all at once. Computer simulations reveal that small galaxies formed first, shortly after the Big Bang. Over billions of years, they merged into larger structures. The Milky Way and Andromeda each grew by consuming dozens or hundreds of smaller galaxies. The dwarf galaxies we see today are survivors, small enough to resist merging so far, but most will eventually be absorbed. Gravity holds the local group together, and that gravity is dominated by dark matter. The visible stars in all 50 galaxies contribute only a fraction of the total mass. Most of the group's mass is invisible, spread throughout the volume in a web of dark matter that keeps everything bound. Without dark matter, the local group would have dispersed long ago, its members flung apart by the expansion of space. The center of mass for the local group sits somewhere between the Milky Way and Andromeda. Both galaxies orbit around this point, which is why they are moving toward each other. They are not falling into each other randomly. They are following gravitational orbits that will eventually bring them together. The collision is not a question of if, but when. As the universe continues expanding, the space between galaxy groups grows. The local group will become increasingly isolated from other groups. Already, the nearest groups sit millions of light-years away. The Maffei group lies around 10 million light-years distant, heavily obscured by dust in the plane of the Milky Way. The Sculptor group sits 11 million light-years away. These neighboring groups are receding from us as space expands. Eventually, the local group will merge into a single galaxy. Simulations suggest that in 100 billion years, the Milky Way, Andromeda, Triangulum, and most dwarf members will have combined. From the outside, observers would see one giant elliptical galaxy where 3 spirals once existed. From the inside, future inhabitants might look out and see almost nothing. The nearest galaxies will have receded beyond the cosmic horizon, but for now, the local group remains part of a larger structure. We sit near the edge of a vast collection of galaxy groups and clusters, an enormous flattened disk of galaxies that makes the local group look like a single grain of sand on a beach. This structure dominates our corner of the universe. The Milky Way and Andromeda are on a collision course, rushing toward each other at roughly 250,000 miles per hour. This velocity was confirmed through precise measurements of Andromeda's motion across the sky and its approaching redshift. The impact will occur in approximately 4 billion years, give or take a few 100 million years depending on the exact trajectories. Imagine watching this collision from outside both galaxies. At first, the two spirals approach slowly, their shapes still intact. As they draw closer, gravity begins pulling tidal tails from both. Long streams of stars stretch between them, forming bridges of light across the void. The galaxies deform, their spiral arms distorting as they feel each other's gravitational pull from millions of light years away. Then they touch. The leading edges of their dark matter halos overlap. Stars from one galaxy pass through regions of the other, but individual stars almost never collide. Space between stars is so vast that collisions are statistically unlikely, even during a galactic merger. What does collide is gas. Enormous clouds of hydrogen slam into each other at incredible speeds, compressing and heating. The compression triggers waves of star formation, lighting up both galaxies with brilliant new stars. The first pass takes millions of years. The galaxies interpenetrate, their centers passing within tens of thousands of light years of each other. Gravity twists both structures, pulling stars into new orbits. Some stars gain enough velocity to escape both galaxies entirely, flung out into intergalactic space to wander alone forever. Others fall toward the center, where the two supermassive black holes begin their own deadly dance. The galaxies separate after the first pass, but they do not escape. Gravity pulls them back. Over the next few 100 million years, they swing around their common center of mass and collide again. Each collision strips away more stars, creating enormous tidal tails stretching for hundreds of thousands of light years. These tails mark where stars have been pulled from their home galaxies and left stranded in the space between. After multiple passes, the galaxies lose their spiral structures. The organized rotation that maintained their arms breaks down. Stars begin orbiting randomly, creating a spherical cloud instead of a disk. This is how elliptical galaxies form. They are the products of major mergers, their chaotic, stellar orbits evidence of violent pasts. Finally, the two galactic cores merge. The supermassive black holes at each center sink toward each other, pulled by gravity and dynamical friction. When they come close enough, they begin orbiting each other, spinning faster and faster as they lose energy to gravitational waves. Confirmed by recent detections of gravitational waves from merging black holes, we know this process happens, though we have never observed supermassive black holes merging directly. The black holes spiral inward for millions of years. Then, in the final moments, they merge in a cataclysm that releases more energy in gravitational waves than all the stars in the galaxy emit in light. The merged black hole, weighing hundreds of millions of times what our star weighs, sits at the heart of the new elliptical galaxy. Our solar system will likely survive. The chances of a direct stellar collision are tiny, but our position within the galaxy will change. We might end up farther from the center, or we might be pulled inward. There is even a small chance we get ejected entirely, thrown out into intergalactic space during one of the chaotic passes. By the time the merger finishes, the night sky will look completely different. Andromeda will no longer be a distant smudge. During the height of the collision, it will dominate the sky, stretching across dozens of degrees as the two galaxies intertwine. New stars will blaze to life in massive star-forming regions. And then, slowly, the chaos will settle into a new stable configuration. The result will be an elliptical galaxy, sometimes called Milky Way. It will contain all the stars from both the Milky Way and Andromeda, well over 1 trillion stars in total. But even this giant will be just one galaxy among many, and it will belong to a structure far larger than itself. 54 million light-years away, in the direction of the constellation Virgo, lies a massive concentration of galaxies. The Virgo cluster contains over 2,000 galaxies packed into a region about 15 million light-years across. Giant elliptical galaxies dominate its core, the largest being Messier 87, a monster galaxy with a supermassive black hole weighing 6.5 billion times what our star weighs. The Virgo cluster is not isolated. Surrounding it, spread across a vast, flattened disk, sit at least 100 other galaxy groups and clusters. This entire structure forms the Virgo supercluster, sometimes called the local supercluster because the local group sits near its edge. The supercluster spans roughly 110 million light-years from side to side, confirmed through extensive mapping of galaxy positions and velocities. Our local group occupies a position far from the center, about 65 million light-years from the Virgo cluster. We sit on the outskirts of this structure, near the edge of the disk. From our vantage point, the Virgo cluster's gravity tugs on us, pulling the local group toward it at a few hundred miles per second. This motion is called the Virgocentric flow, and it has been confirmed through precise measurements of galaxy velocities. The Virgo supercluster is not spherical. It forms a flattened ellipsoid like a disk or pancake. The galaxies concentrate along this disk, with relatively few galaxies in the regions above and below. This flattened shape results from how the structure formed. Dark matter collapsed first, creating a scaffolding, and galaxies formed where dark matter was densest. Between the concentrations of galaxies lie voids. These are vast regions of nearly empty space, sometimes tens of millions of light-years across, containing very few galaxies. The voids and filaments together form what astronomers call the cosmic web. Galaxies cluster along the filaments, which outline the surfaces of enormous bubbles. The voids are the interiors of these bubbles, mostly empty. The Virgo supercluster contains roughly the mass equivalent of 100 billion Milky Way galaxies. This includes both visible matter and dark matter. Most of that mass is dark matter, spread throughout the volume in a halo that extends beyond the visible galaxies. The luminous matter, all the stars and gas we can see, represents only about 15% of the total mass. Despite its enormous size, the Virgo supercluster is not gravitationally bound as a single structure. The expansion of the universe is pulling its outer regions apart. Only the densest concentrations, like the Virgo cluster itself, are compact enough to resist expansion. The rest of the supercluster will slowly disperse over billions of years as space expands between galaxy groups. This was a surprising discovery made in recent decades. Astronomers once thought superclusters were gravitationally bound objects, like scaled-up versions of galaxy clusters. But detailed measurements revealed otherwise. The Virgo supercluster is not a stable structure. It is a temporary concentration of galaxies that happens to exist in our current epoch. In the deep future, it will no longer be recognizable as a distinct entity. Yet even this temporary structure is merely one thread in a larger tapestry. Recent observations revealed that the Virgo supercluster is part of an even more immense concentration of galaxies, one that makes the supercluster look small. The Virgo supercluster contains a mass equivalent to 100 billion Milky Way galaxies. Let that number settle. 100 billion copies of our entire galaxy, all the stars and gas and dark matter, compressed into a single structure 110 million light-years across. But the Milky Way itself contains up to 400 billion stars. Multiply 100 billion galaxies by 400 billion stars each, and you get a number so large it loses meaning. 40 sextillion stars, give or take. That is 40, followed by 21 zeros. More stars in the Virgo supercluster than grains of sand on every beach across continents. Yet this number mostly comes from theoretical calculations, not direct observation. Astronomers cannot count every star in the supercluster. Most are too distant and faint. Instead, they measure the total mass by observing how galaxies move. The velocities of galaxies within the supercluster reveal the gravitational forces acting on them. More mass means stronger gravity, which means higher velocities. By mapping these motions, scientists determined that the supercluster's visible matter accounts for only a fraction of its total mass. Dark matter contributes roughly 85%. This dark matter forms an enormous halo surrounding and permeating the entire supercluster. It does not emit light, but its gravity shapes the paths of every galaxy within the structure. The distribution of mass within the Virgo supercluster is uneven. The Virgo cluster at the center contains a disproportionate amount, roughly 10 to the 14th times the mass of our star. This central concentration pulls on surrounding galaxy groups, creating the Virgo-centric flow that drags the local group toward the cluster at hundreds of miles per second. If we could see dark matter, the supercluster would look like a vast web of interconnected filaments. Galaxies would appear as bright nodes where filaments intersect, with tendrils of dark matter stretching between them. The voids would be visible as enormous bubbles, their surfaces traced by galaxy-filled filaments. But the Virgo supercluster is not the end of the hierarchy. It exists as part of an even larger structure, one that dwarfs everything we have discussed so far. In 2014, a team of astronomers announced a discovery that redefined our cosmic address. Using a new technique to map galaxy flows, they revealed that the Virgo supercluster is merely one lobe of a much greater concentration. This larger structure contains approximately 100,000 galaxies, including the Milky Way, Andromeda, and the entire Virgo supercluster. It spans 520 million light-years from end to end, making it one of the largest structures in the known universe. The mass is equivalent to 100,000 Milky Way galaxies, though estimates vary. The discovery came from mapping not where galaxies are located, but where they are moving. Galaxies do not move randomly through space. They fall toward concentrations of mass along paths determined by gravity. By tracing these paths backward, astronomers identified the gravitational basin that holds our local region of the universe together. This immense structure has a center, a gravitational focal point toward which everything nearby is falling. The Virgo cluster is falling toward it. The local group is falling toward it. Thousands of galaxy groups and clusters across hundreds of millions of light-years are all being pulled in the same direction. That gravitational center has a name, and it represents one of the great mysteries in modern astronomy. Something massive is pulling our galaxy. The Milky Way, the local group, the entire Virgo supercluster, all moving in the same direction at over 1 million miles per hour. Astronomers call the destination the Great Attractor, and for decades, it remained one of the most puzzling anomalies in cosmology. The evidence for this motion came from observations of the cosmic microwave background, the faint radiation left over from the Big Bang. This radiation should appear uniform in all directions if we were at rest relative to the cosmos. But measurements revealed a dipole pattern, with the radiation slightly hotter in one direction and cooler in the opposite direction. This pattern indicates motion. We are moving through space, and the motion creates a Doppler shift in the background radiation. Astronomers calculated our velocity and direction. The entire local supercluster is falling toward a region of space about 250 million light-years away, in the direction of the constellations Hydra and Centaurus. The mass required to create this gravitational pull must be enormous, equivalent to tens of thousands of Milky Way galaxies concentrated in one region. But looking in that direction revealed a problem. The plane of the Milky Way obscures the view. Dust and stars in our own galaxy block optical light from that region of space, creating what astronomers call the zone of avoidance. Early attempts to observe the Great Attractor directly saw very little. A few galaxy clusters were detected, but not enough mass to explain the observed motion. Radio and X-ray observations eventually penetrated the dust. They revealed several massive galaxy clusters in the region, including the Norma cluster and the Centaurus cluster. Together, these clusters contain enough mass to account for some of the gravitational pull, but not all of it. The Great Attractor appeared to be more diffuse than a simple cluster, spread across a larger volume of space. The mystery deepened when astronomers realized the motion does not stop at the Great Attractor. The Great Attractor itself is moving, pulled by an even larger concentration of mass farther away. This second structure, called the Shapley supercluster, sits 650 million light-years distant and contains over 8,000 galaxies. It is one of the most massive structures in the observable universe, and its gravity influences galaxy motions across enormous distances. The discovery of these massive structures led to a broader understanding. Galaxies do not move randomly through the universe. They flow along paths determined by the distribution of matter, both visible and dark. These flows converge toward high-density regions and diverge from low-density voids. By mapping the flows, astronomers can reconstruct the underlying mass distribution, even where direct observations are difficult. In 2014, this technique revealed that the Great Attractor is not a single, isolated mass concentration. It is the central region of an enormous structure containing the Virgo supercluster, the Hydra Centaurus region, and several other superclusters. This greater structure has been confirmed through multiple independent analyses of galaxy velocities and positions. The Great Attractor region marks the gravitational center of this vast basin. Everything within 520 million light-years falls toward it, pulled by the combined gravity of all the matter within the structure. The Virgo supercluster, which once seemed like the dominant feature in our region of the universe, is merely one part of this larger whole. This discovery forced a re-evaluation of what constitutes a distinct structure. The Virgo supercluster is not gravitationally bound and will eventually disperse, but the larger structure of which it is a part may represent a true dynamical system, at least temporarily. That larger structure has a name, given to it by the astronomers who mapped its extent. They called it Laniakea. The name comes from Hawaiian, meaning immense heaven or open skies. Laniakea supercluster, confirmed in 2014 through detailed mapping of galaxy velocities, spans 520 million light-years from end to end. It contains approximately 100,000 galaxies, including our own, all moving in coordinated flows toward a common gravitational center. This is our cosmic address on the largest scales currently mapped. Earth sits inside the solar system, which orbits within the Milky Way, which belongs to the local group which lies near the edge of the Virgo supercluster, which is one lobe of Laniakea. Each level of this hierarchy increases in size by factors of millions or billions. Laniakea is not a single compact object. It is a sprawling web of interconnected filaments and nodes, with galaxies concentrated along threads that outline enormous voids. The structure resembles a biological system, with arteries of galaxies feeding into larger concentrations. The Virgo supercluster forms one major branch. The Hydra Centaurus region forms another. Several other superclusters contribute additional mass. The total mass of Laniakea equals approximately 100 quadrillion times the mass of our star. That number, 1 followed by 17 zeros, represents the combined mass of all galaxies, all gas clouds, and all dark matter within the structure. Dark matter contributes the vast majority, forming an invisible scaffolding that holds everything together. Galaxies within Laniakea move in coherent patterns. Instead of expanding away from each other uniformly, they flow along preferred directions, converging toward the densest regions. These flows trace the underlying dark matter distribution. Where dark matter is concentrated, galaxies fall inward. Where dark matter is sparse, galaxies drift outward into voids. The boundary of Laniakea is not a physical edge. It is defined by the limit of the gravitational basin. Beyond this boundary, galaxies flow toward other attractors, other gravitational centers. The adjacent basin belongs to another supercluster, the Perseus-Pisces supercluster, which pulls on galaxies in its own region. Between these basins, at the watershed boundary, galaxy motions become ambiguous. Laniakea itself is not gravitationally bound. Detailed analysis reveals that the expansion of the universe is pulling its outer regions apart faster than gravity can hold them. The structure will disperse over billions of years. Only the densest cores, like the Great Attractor region, might remain bound. The rest will be carried away by cosmic expansion. This raises a question about whether Laniakea should be called a supercluster at all. Traditional definitions require structures to be gravitationally bound. Laniakea does not meet this criterion. It is more accurately described as a temporary concentration of galaxies that share a common motion pattern in the current epoch. Future cosmologists may see the galaxies now in Laniakea, scattered across much larger distances. Yet, despite its transient nature, Laniakea represents our place in the universe on scales approaching the limits of what we can currently map. Beyond Laniakea lie other structures, other basins of galaxies flowing toward their own centers. The universe at the largest scales resembles an ocean with countless currents and eddies, each containing billions of galaxies. The discovery of Laniakea changed how astronomers think about cosmic structure. Instead of defining structures by their appearance, we now define them by their dynamics. A supercluster is not just a group of galaxy clusters that happen to be near each other. It is a region of space where galaxies share a common gravitational influence. This dynamic view reveals patterns invisible to traditional surveys. The cosmic web becomes clear when you map galaxy velocities. Filaments appear where matter flows along dense threads. Voids emerge where galaxies accelerate away from underdense regions. And at the intersections of filaments, massive concentrations of galaxies form the nodes that anchor the web. But even the cosmic web, spanning billions of light-years, represents only what we can observe. The actual universe extends beyond our view, perhaps infinitely, and its structure continues beyond Laniakea, forming patterns we are only beginning to comprehend. The universe is not random. Galaxies do not scatter evenly through space. Instead, they arrange themselves in an intricate network of filaments and sheets, separated by vast voids. This pattern, confirmed through decades of galaxy surveys, is called the cosmic web, and it represents the largest scale structure in the universe. The cosmic web formed from tiny density fluctuations in the early universe. Shortly after the Big Bang, matter was distributed almost uniformly, with only minuscule variations in density from place to place. These variations, confirmed by observations of the cosmic microwave background, served as seeds for structure formation. Gravity amplified the variations. Regions slightly denser than average pulled in more matter, becoming denser still. Regions slightly less dense lost matter to their surroundings, becoming voids. Over billions of years, this process created a hierarchy of structures. Small clumps merged into larger ones. Galaxies formed where dark matter accumulated. Those galaxies gathered into groups, then clusters, then superclusters, all following the underlying dark matter distribution. The result is a web of filaments. These cosmic threads span hundreds of millions of light-years in length, but they are only a few million light-years thick. Galaxies concentrate along the filaments like beads on a string. Where multiple filaments intersect, massive galaxy clusters form. These clusters can contain thousands of galaxies in regions tens of millions of light-years across. Between the filaments lie the voids. These are enormous bubbles of nearly empty space, typically 50 to 100 million light-years in diameter. Some voids reach 300 million light-years across. They contain very few galaxies, and those that exist tend to be small dwarfs. The voids are not completely empty, as they contain some dark matter and gas, but their density is far below the cosmic average. The cosmic web is not static. It evolves as the universe expands. Filaments stretch and thin. Voids grow larger. Galaxies within filaments gradually fall toward the nearest cluster, pulled by gravity. Over time, the contrast between dense and empty regions increases. The rich get richer while the poor get poorer, in terms of mass distribution. Simulations reproduce this structure remarkably well. Computer models start with dark matter particles distributed according to the density fluctuations observed in the cosmic microwave background. They evolve the particles forward in time using gravitational physics. The result matches what surveys observe. Filaments form, voids appear, clusters develop at the nodes. The cosmic web emerges naturally from gravity, acting on slightly uneven initial conditions. Observations confirm the simulations. Large-scale surveys like the Sloan Digital Sky Survey mapped millions of galaxies across a significant fraction of the sky. The data revealed the cosmic web in exquisite detail. Filaments and voids became visible. Superclusters appeared as concentrations along the filaments. The universe showed clear structure on scales approaching 1 billion light-years. The cosmic web is shaped by dark matter. Luminous matter, the stars and gas we can see, follows where dark matter leads. Dark matter filaments formed first. Galaxies assembled within them later. This is why the distribution of galaxies traces the cosmic web. They are simply marking where dark matter is concentrated, but the web itself rests on an even larger pattern. The filaments are not infinite. They have characteristic lengths and spacings. This scale, roughly 300 million light-years, represents the typical size of structures that formed from the primordial density fluctuations. Smaller fluctuations created smaller structures. Larger fluctuations created larger ones. The peak in the fluctuation power spectrum corresponds to structures about this size. The cosmic web extends throughout the observable universe. Every direction we look, we see the same pattern: filaments and voids, clusters and superclusters. The structure is universal. This uniformity tells us that the physical processes creating the web operated the same way everywhere, reinforcing the cosmological principle that the universe is homogeneous on the largest scales. Yet between the filaments, in the vast voids, lies something that challenges our understanding of structure. These empty regions are larger than anything else in the universe. The Boötis void stretches 330 million light-years across. Inside this enormous bubble of space, astronomers have found only about 60 galaxies. In a typical region of that size, you would expect to find roughly 10,000 galaxies. The void is 99% empty compared to the cosmic average. Voids dominate the volume of the universe. While filaments and clusters contain most of the galaxies, they occupy a relatively small fraction of total space. Voids, by contrast, fill most of the universe's volume. If you picked a random point in space, you would most likely find yourself inside a void, hundreds of millions of light-years from the nearest galaxy cluster. The Boötis void is not unique. Surveys have revealed dozens of similar structures. The Sculptor void spans similar distances. The Eridanus supervoid measures nearly 1 billion light-years across, one of the largest known structures of any kind. These voids are not perfectly empty. They contain some dark matter and gas, and a handful of isolated galaxies float in their interiors. But their density is far below average. How do voids form? They result from the same process that creates filaments and clusters, just in reverse. Regions that started slightly underdense after the Big Bang lost matter to their surroundings. As denser regions pulled in material, the underdense regions became more depleted. Gravity emptied them out over billions of years. The process is confirmed through simulations, which show voids naturally emerging from the gravitational evolution of matter. Inside voids, the expansion of the universe proceeds slightly faster than average. With less mass to slow it down, space expands more freely. This creates an outflow pattern. Galaxies near the edges of voids accelerate away from the centers. Over time, this pushes the few remaining galaxies toward the void boundaries, making the interiors even emptier. The galaxies that do exist inside voids tend to be different from those in dense regions. They are often younger, with more active star formation. This makes sense. In clusters, galaxies collide and merge frequently, using up their gas supplies and quenching star formation. Inside voids, galaxies remain isolated. They retain their gas longer and continue forming stars at a steady pace. Voids also affect the cosmic microwave background. Light from the early universe passes through voids on its way to us. As photons fall into a void, they gain energy. As they climb back out, they lose energy. If the void size did not change, these effects would cancel. But because the universe expands, voids grow during the photon's transit. The photon loses more energy climbing out than it gained falling in. This creates a cold spot in the cosmic microwave background, a shadow of the void. One such cold spot exists in the direction of the Eridanus supervoid. Observations confirm that the temperature in that region is slightly lower than the surrounding background. The deficit matches what we expect if a supervoid lies along the line of sight. This provides independent evidence for the void's existence beyond just the missing galaxies. Voids challenge some cosmological models. The largest voids are near the limits of what standard theories predict. If structures too large, compared to what initial conditions allow form, It suggests something unexpected happened during the universe's early evolution. Most voids fit within predictions, but the biggest ones push the boundaries. The existence of voids also creates a philosophical question. If most of the universe's volume is nearly empty, what does it mean to say the universe is filled with matter? Matter concentrates in tiny threads and nodes, like foam on an ocean's surface. The bulk of space contains almost nothing. We live in one of the rare dense regions, on a planet in a galaxy in a filament. Most of the cosmos is silence and darkness. Yet, even the largest voids are tiny compared to the observable universe, and the voids themselves are part of a structure that spans farther than we can yet comprehend. The cosmic web extends to the limits of our observations, and beyond it lies more web, more structure, continuing outward past the cosmic horizon. But understanding how all this structure holds together requires understanding the invisible scaffolding beneath it. 85% of the matter in the universe is invisible. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation in any way we can detect. Yet it dominates the universe's mass budget, and without it, nothing we see could exist. Astronomers call it dark matter, and its existence is confirmed through multiple independent observations. The evidence began with galaxy rotation curves. Stars at the edges of spiral galaxies orbit faster than they should if only visible matter existed. According to Newton's laws, objects farther from a mass center should orbit more slowly, yet stars at the outer edges of galaxies maintain high velocities. This implies that additional unseen mass extends far beyond the visible disk, holding those stars in their fast orbits. Galaxy clusters provided more evidence. The velocities of galaxies within clusters are too high for the visible matter to hold them together. Clusters should fly apart unless additional mass supplies extra gravity. Observations of hot gas in clusters confirmed this. The gas temperature and distribution require far more mass than we see in stars and gas alone. Gravitational lensing sealed the case. Light from distant galaxies bends as it passes through massive structures. The amount of bending depends on the total mass along the line of sight, regardless of whether that mass emits light. Observations show that galaxy clusters bend light far more than their visible matter alone could explain. The lensing maps reveal dark matter halos surrounding and permeating the clusters. Dark matter forms the scaffolding of the cosmic web. Computer simulations that include only dark matter produce structures remarkably similar to what we observe. The simulations start with tiny density fluctuations. Dark matter particles collapse into filaments and nodes under gravity. Where dark matter concentrates, it creates potential wells. Normal matter falls into these wells and forms galaxies. The visible universe traces the invisible dark matter distribution. What is dark matter made of? We do not know. It must be something that interacts gravitationally but not electromagnetically. Particles like this do not exist in the standard model of particle physics, which means dark matter is likely something new, something not yet discovered in laboratory experiments. Candidates include weakly interacting massive particles, axions, or perhaps primordial black holes. Experiments around the world search for direct detection, but so far, dark matter remains elusive. Despite not knowing its composition, we can map where dark matter is located. Gravitational lensing creates detailed maps of dark matter distribution in galaxy clusters. These maps show dark matter concentrated in the same regions as galaxies, but extending farther. Dark matter halos around clusters span tens of millions of light-years, far larger than the visible galaxy distribution. On larger scales, dark matter defines the cosmic web. Filaments are primarily dark matter, with galaxies marking their locations. Voids are regions where dark matter is sparse. The structure of the universe at the largest scales is the structure of dark matter distribution. Visible matter is just a tracer, a small component following the dominant invisible mass. Dark energy is not the same as dark matter. Dark energy is even more mysterious. It is a property of space itself, causing the expansion of the universe to accelerate. While dark matter provides gravity that pulls structures together, dark energy pushes them apart. Dark matter forms structure. Dark energy disrupts it. The balance between these two invisible components determines the fate of the universe. Current measurements indicate that dark energy makes up about 68% of the universe's total energy density. Dark matter contributes about 27%. Normal matter, everything we can see and touch, amounts to only 5%. The universe consists mostly of things we do not understand. This invisible architecture extends throughout the observable universe. Dark matter filaments connect all structures. Dark energy fills all space. Together, they shape the cosmos on scales from individual galaxies to the largest superclusters. Everything we observe is a consequence of their influence. Yet, even with dark matter and dark energy dominating, visible structures exist that dwarf the Milky Way by factors that seem impossible. IC 1101 sits over 1 billion light-years away, so distant that its light has traveled for more than 1 billion years to reach us. It is the largest known galaxy, a supergiant elliptical that spans approximately 4 million light-years from edge to edge. That makes it 40 times wider than the Milky Way's visible disk, and twice as wide even including our dark matter halo. This galaxy contains over 100 trillion stars. That number, 100 followed by 12 zeros, represents more than 200 times the Milky Way's stellar population. If every star in IC 1101 had a planet, and every planet had a moon, the total number of worlds would still exceed comprehension. The galaxy's mass equals approximately 100 trillion times the mass of our star, making it one of the most massive single galaxies known. IC 1101 did not form in isolation. It grew by consuming other galaxies over billions of years. Elliptical galaxies, like this one, are thought to be the products of major mergers. When two spiral galaxies collide, their organized rotation breaks down. The merger scrambles stellar orbits, creating a spherical cloud instead of a disk. Repeated mergers build mass, and IC 1101 has likely undergone countless such collisions. The galaxy's core contains a supermassive black hole weighing approximately 66 billion times what our star weighs. This is one of the most massive black holes ever measured. By comparison, the black hole at the Milky Way's center weighs only 4 million times our star's mass. IC 1101's black hole is 16,000 times more massive. Its gravitational influence extends across thousands of light-years, dominating the galaxy's central region. IC 1101 sits near the center of the Abell 2029 galaxy cluster, one of the richest clusters in the observable universe. Its position at the cluster's core is not coincidental. The most massive galaxies tend to occupy cluster centers because they sink to the bottom of the gravitational well through a process called dynamical friction. As IC 1101 moves through the cluster, it interacts gravitationally with surrounding galaxies, slowly losing orbital energy and settling toward the center. From IC 1101, the night sky would look strange. The galaxy's outer regions are sparse, with stars separated by vast distances. An observer in those outer reaches might see a sky darker than ours, with only distant points of light from neighboring galaxies. But toward the center, the sky would blaze. Stars pack densely in the core, creating a diffuse glow bright enough to cast shadows even from light years away. IC 1101 represents an extreme, but it is not unique. Other supergiant ellipticals exist throughout the universe. Messier 87 in the Virgo cluster, though smaller than IC 1101, still dwarfs the Milky Way. These monsters reside at the centers of massive clusters, grown fat on the galaxies they have consumed. The existence of such large galaxies tells us about structure formation in the universe. Galaxies grow through mergers and accretion. Small galaxies formed first, shortly after the Big Bang. Over billions of years, they merged into larger ones. The process continues today. IC 1101 is still growing, slowly consuming dwarf galaxies that wander too close. But most galaxies are not giants like IC 1101. For every supergiant elliptical, billions of dwarf galaxies exist, too small and faint for most surveys to detect. These tiny galaxies vastly outnumber the giants, and they reveal a different side of the cosmic hierarchy. Most galaxies in the universe contain fewer than 1 billion stars. These dwarf galaxies outnumber giants like the Milky Way by factors of hundreds or thousands to one. The small Magellanic Cloud, visible from Earth's southern hemisphere, holds only a few billion stars and spans just 7,000 light-years. Yet even this relatively bright dwarf represents the upper end of the size range. The faintest dwarf galaxies discovered contain only a few thousand stars total, spread across regions a few hundred light-years wide. These ultra-faint dwarfs emit so little light that they remained hidden until recent surveys with advanced telescopes detected them. The Segway 1 dwarf galaxy, orbiting the Milky Way, contains roughly 1,000 stars. An observer inside would see a sparse scattering of points against the darkness, barely enough to qualify as a galaxy at all. Dwarf galaxies present a puzzle. According to cosmological simulations, far more small dark matter halos should exist than we observe dwarf galaxies. The models predict thousands of small halos around large galaxies like ours, yet we find only dozens of dwarfs. This discrepancy is called the missing satellites problem, and it suggests either our models are incomplete or most dwarf galaxies are too faint to detect. Recent surveys support the second explanation. Advanced telescopes keep discovering new ultra-faint dwarfs around the Milky Way and Andromeda. Each survey that pushes to fainter limits finds more. The evidence suggests that thousands of dwarf galaxies orbit nearby, most invisible to current instruments. When the next generation of telescopes comes online, the census will likely explode. Dwarf galaxies have dominated cosmic history in terms of numbers. In the early universe, shortly after the first stars formed, small galaxies appeared everywhere. These proto-galaxies contained only millions of stars each, but they were abundant. Over time, they merged into larger structures. The dwarfs we see today are survivors, small enough to resist merging so far, though most will eventually be consumed. Dark matter dominates dwarf galaxies even more than it dominates large ones. Some ultra-faint dwarfs have mass-to-light ratios exceeding 1,000, meaning they contain 1,000 times more mass in dark matter than in stars. They are essentially dark matter halos with a tiny sprinkling of stars. Without dark matter, these galaxies would not have enough gravity to hold together. Stars would escape into intergalactic space. Dwarf galaxies reveal the lower limit of galaxy formation. Below a certain dark matter halo mass, galaxies cannot form at all. The smallest halos lack sufficient gravity to pull in and retain gas. Starlight and cosmic radiation heat the gas, preventing it from cooling and collapsing into stars. Only halos above a threshold mass can overcome these effects and form visible galaxies. This threshold explains why we do not see galaxies smaller than the ultra-faint dwarfs. The physics of gas cooling and star formation sets a minimum scale. Below that scale, dark matter halos exist but remain dark, devoid of stars. These invisible halos populate the universe, detectable only through their gravitational effects on visible matter. The combined mass of all dwarf galaxies likely exceeds that of giant galaxies. They are individually tiny, but collectively numerous. If you summed the total stellar mass in all dwarfs throughout the observable universe, it might rival or exceed the mass in large galaxies like ours. The universe's population is bottom-heavy, with most galaxies clustered at the small end of the size distribution. Yet, even as dwarf galaxies dominate the population count, they fade into insignificance when facing the force that controls the fate of the cosmos itself. The universe is not just expanding, it is accelerating. This discovery, confirmed in 1998 through observations of distant supernovae, shocked cosmologists. The expansion should be slowing down due to gravity, pulling everything back together. Instead, Galaxies are flying apart faster and faster. The evidence came from Type Ia supernovae, exploding white dwarf stars that serve as cosmic distance markers. These explosions reach consistent peak brightnesses, allowing astronomers to calculate distances by measuring how bright they appear. Comparing distances with redshifts reveals the expansion rate at different cosmic epochs. Distant supernovae appeared fainter than expected. This means they are farther away than they should be if the expansion rate were constant or decreasing. The only explanation is that the expansion has accelerated since those supernovae exploded billions of years ago. Space itself is stretching faster now than it did in the past. This acceleration requires something new, something that pushes space apart instead of pulling it together. Cosmologists call it dark energy, and it makes up roughly 68% of the universe's total energy density. Unlike dark matter, which clumps and creates gravity, dark energy spreads uniformly through space and generates a repulsive force. Dark energy's nature remains mysterious. The simplest explanation is that it represents the energy of empty space itself, sometimes called vacuum energy or the cosmological constant. Quantum field theory predicts that empty space should have energy, though calculations yield values wildly different from what we observe. The discrepancy, called the cosmological constant problem, is one of the biggest unsolved puzzles in physics. Regardless of its nature, dark energy's effects are clear. It makes the expansion accelerate. At early times, when the universe was smaller and denser, dark energy contributed little compared to matter. Gravity dominated, slowing the expansion. But as the universe grew and matter spread out, dark energy became increasingly important. About 5 billion years ago, confirmed through multiple independent measurements, dark energy's repulsive effect exceeded gravity's attractive pull. The expansion began accelerating. This acceleration has profound consequences for the universe's future. Structures that are not gravitationally bound will be pulled apart. Galaxy clusters will remain intact because their internal gravity is strong enough to resist, but superclusters will disperse. The cosmic web will stretch until filaments snap. Eventually, even galaxy groups might be torn apart, leaving each galaxy isolated. The Milky Way and Andromeda will still collide because they are gravitationally bound and close enough that dark energy cannot overpower their attraction. But more distant galaxies are already receding beyond our reach. Light they emit today will never arrive because space between us expands too fast. They are crossing the cosmic horizon, disappearing from the observable universe forever. In the far future, observers in our merged galaxy will look out and see almost nothing. The nearest galaxies beyond our local group will have redshifted into invisibility. The cosmic microwave background will fade to undetectable levels. Space will appear empty and black. Future civilizations might conclude they live alone in a static, unchanging universe, unaware of the billions of galaxies that once filled the sky. Dark energy also affects the shape of space. Measurements of the cosmic microwave background and galaxy distributions indicate the universe is geometrically flat, or very nearly so. This flatness is maintained partly by dark energy's influence. If dark energy's strength were different, the universe might be curved in ways that would make large-scale structure formation impossible. The acceleration sets an ultimate limit on what we can observe. Even if we wait forever, there are galaxies we will never see. Their light will never reach us. They exist beyond the cosmic horizon, in regions of space forever disconnected from our own. But this raises a question that has haunted astronomers since Edwin Hubble first measured the expansion. If galaxies beyond a certain distance are unreachable, what defines the edge of observation? 46 billion light-years. That distance marks the edge of the observable universe in any direction from Earth. Beyond that limit, nothing can be detected. Light from farther regions has not had time to reach us since the Big Bang, and due to acceleration, it never will. This creates a spherical boundary around us, sometimes called the particle horizon. Everything inside this sphere is potentially observable. Everything outside remains forever invisible. The boundary is not a physical wall. It is a consequence of the universe having a finite age and the finite speed of light. The cosmic horizon shifts with time. As the universe ages, light from more distant regions reaches us for the first time. Every second, the observable universe grows. New galaxies appear at the edge of visibility, their ancient light finally completing its journey across space. But this growth has a limit. Due to acceleration, there is a maximum distance light can ever travel to reach us, no matter how long we wait. This defines a different horizon, sometimes called the cosmic event horizon. It sits at roughly 62 billion light-years, confirmed through cosmological calculations. Galaxies currently beyond this distance are receding faster than light can close the gap. Their light will never arrive. This creates a strange asymmetry. We can see galaxies now beyond the event horizon because we are observing light they emitted billions of years ago when they were closer. But we will never see what they look like today or what they become in the future. Those galaxies have crossed a boundary and entered a region of space causally disconnected from ours. From those distant galaxies' perspective, we have crossed their event horizon. Observers there can see our galaxy as it appeared billions of years ago, but they will never receive light showing what we become. We exist in each other's past, but not each other's future. The expansion of space has severed the connection. The horizon creates an isolation more absolute than mere distance. Even if we could travel at the speed of light, we could never reach galaxies beyond the event horizon. The space between us expands faster than we could cross it. Attempting the journey would be like running on a treadmill that accelerates faster than you can run. You would never make progress toward your destination. This raises philosophical questions about the nature of existence. Do galaxies beyond our horizon exist in any meaningful sense if we can never interact with them or receive information from them? Physics suggests they do. The laws of nature do not change at the horizon. Space continues beyond it, but we can never verify this through observation. The horizon also affects our ability to understand cosmology. We sample only a finite region of space. The observable universe might not be representative of the whole. If the universe is infinite, we see an infinitesimally small fraction. Statistical fluctuations in our region might mislead us about conditions elsewhere. What we call universal laws might only be local laws that happen to apply within our observable bubble. Measurements of the cosmic microwave background provide some reassurance. The radiation is remarkably uniform across the sky, suggesting the universe is homogeneous on large scales. If our region were atypical, we would expect to see larger variations. The uniformity implies that what we observe is representative, at least statistically. Yet the horizon limits what we can ever know. Questions about the universe's total size, its overall shape, and what lies beyond the observable region may be fundamentally unanswerable. We can theorize and extrapolate, but direct observation is impossible. The cosmos extends beyond our reach, perhaps infinitely, and we can only study the small portion accessible to us. This accessible portion contains 2 trillion galaxies spanning 93 billion light-years. That is an immense sample, but it might represent only a tiny fraction of reality. Most of the universe lies beyond the horizon, unknown and unknowable. We see roughly 3% of the total universe. This estimate comes from comparing the size of the observable universe, 93 billion light-years across, with theoretical calculations of the entire cosmos. If cosmic inflation occurred as models predict, the full universe should be vastly larger than what we can observe. Cosmic inflation was a period in the universe's first fraction of a second when space expanded exponentially fast. This rapid expansion stretched the universe from subatomic scales to scales far larger than the current observable region. Observations of the cosmic microwave background confirm that inflation likely occurred based on the patterns in temperature fluctuations across the sky. If inflation expanded the universe by at least 60 E-folds, as most models suggest, the total size would be immense. An E-fold means multiplying the size by roughly 2.7. 60 E-folds means multiplying by that number 60 times in succession. The result is a universe at least 10 to the power of 26 times larger than the observable region, perhaps far larger. Other estimates approach the question differently. A statistical analysis published in 2011 examined various cosmological models and their likelihood given observational data, the study concluded the universe is at least 250 times larger than the observable portion. That places the minimum diameter at about 7 trillion light-years. Though infinity remains possible, these numbers are speculative because we can only observe what lies within our cosmic horizon. Everything beyond is hidden. We can extrapolate based on the uniformity of what we see and the predictions of inflationary models. But direct verification is impossible. The full universe might be thousands of times larger than we can observe, or millions of times larger, or infinite. An infinite universe has strange implications. If space extends forever, then every possible arrangement of matter exists somewhere. There would be infinite copies of Earth, infinite versions of the Milky Way, infinite instances of every galaxy we observe. Probability becomes meaningless when multiplied by infinity. Everything that can happen does happen, infinitely many times. Most cosmologists consider an infinite universe plausible, perhaps even likely. The geometry of space appears flat according to measurements of the cosmic microwave background. Flat space extending infinitely is the simplest model that fits the data. Alternative models involving curved space that closes back on itself are not ruled out but require fine-tuning to match observations. If the universe is finite, it has a size we could in principle measure if we could observe beyond the horizon, but we cannot. The observable universe defines our sample, and from that sample we must infer the properties of the whole. It is like trying to determine the size of an ocean by examining a single drop of water. The drop's properties tell you about water, but they reveal nothing about the ocean's extent. The Milky Way, from this perspective, becomes almost meaningless in scale. One galaxy among 2 trillion in the observable universe. The observable universe itself, possibly representing less than 1% of the total. The total, potentially infinite. At each level, the previous scale shrinks into insignificance. Yet we live at a level where the Milky Way feels large. Light takes 100,000 years to cross it. That span of time exceeds all of recorded human history by factors of hundreds. We evolved on a planet orbiting an average star in an average location within one galaxy. That single galaxy contains more stars than humans can count, more worlds than we can visit in 1,000,000 lifetimes. The observable universe contains structures so vast that describing them requires new vocabulary: superclusters, filaments, voids spanning hundreds of millions of light years. And all of it might be a tiny fraction of something immeasurably larger. The scale defeats comprehension at every level, but one comparison puts it all in perspective, relating the cosmos back to the world we know. Is the universe infinite? This question divides cosmologists into competing camps, though most evidence leans toward one answer. The geometry of space, confirmed through precision measurements of the cosmic microwave background, appears flat to within 1% accuracy. Flat geometry extending infinitely is the simplest interpretation. An infinite universe has no center and no edge. Every location is equivalent. If you traveled in any direction forever, you would never reach a boundary. Space simply continues. New galaxies, new structures, new regions identical in their statistical properties to ours, but unique in their details. The pattern repeats endlessly. This creates a paradox called the cosmological horizon problem. If the universe is infinite and space is expanding, then regions separated by more than the cosmic horizon have no causal connection. They have never exchanged information, yet they look remarkably similar. The temperature and density of the cosmic microwave background is nearly identical across the entire sky. How can disconnected regions share the same properties? Cosmic inflation solves this paradox. Before inflation, the observable universe was tiny, much smaller than it is now. All regions within the current observable universe were in causal contact back then. They reached the same temperature and density through normal physical processes. Then, inflation stretched that small homogeneous patch into something vastly larger. The regions lost causal contact during inflation, but they retained their initial uniformity. This explanation works whether the universe is finite or infinite. If infinite, Inflation took an already infinite universe and made it exponentially larger, which is mathematically possible. If finite, inflation stretched a small, finite universe into a much larger, finite one. Either way, the result is a cosmos where the observable portion is homogeneous but represents only a small sample of the total. Some models predict the universe is finite but unbounded, like the surface of a sphere. On a sphere, you can travel forever in a straight line and eventually return to your starting point. The surface has no edge, yet it has a finite area. A three-dimensional analog would allow travel through space to eventually loop back, though the distances involved would far exceed the observable universe. Such a model requires space to be curved in specific ways. Measurements of the cosmic microwave background constrain curvature tightly. If space curves back on itself, the curvature must be so gentle that the loop is far larger than the observable universe. We exist inside a sphere, if it is a sphere, with a radius potentially trillions of light years. The curve is too gradual to detect locally. Other models propose a multiverse, where our universe is one bubble in an eternally inflating space. Different bubbles have different properties, different physical constants, different laws. We exist in one bubble, where conditions happen to allow structure formation and life. Beyond our bubble lie countless others, forever unreachable and unobservable. This scenario suggests our universe is finite while the multiverse itself is infinite. All these models remain speculative. We can only observe our local cosmic horizon. Whether space continues infinitely beyond, loops back on itself, or terminates in some unimaginable boundary is unknowable with current technology. Future observations might tighten constraints, but the question may remain forever unanswered. From a practical standpoint, whether the universe is finite or infinite matters little. The observable portion contains enough galaxies, enough stars, enough space to exceed comprehension regardless. 2 trillion galaxies spanning 93 billion light-years already defies human intuition. Whether that represents everything or only a minute sample changes nothing about the immensity we face. The Milky Way contains hundreds of billions of stars. The observable universe contains 2 trillion galaxies. Multiply those numbers. 700 sextillion stars at minimum. Each star potentially hosting planets. The possibilities for worlds, for life, for civilizations multiply into meaninglessness. And if the universe is infinite, those already incomprehensible numbers become truly infinite. Yet despite this overwhelming scale, we can comprehend our position within it. We know our cosmic address. We understand the hierarchy of structures. And comparing that hierarchy to human scales reveals just how small we truly are. Earth measures roughly 8,000 miles in diameter. That seems substantial to creatures walking on its surface. Mountains tower thousands of feet high. Oceans span thousands of miles. Continents stretch across half the globe. From our perspective, Earth is vast. Scale up to the solar system, Earth becomes a blue marble next to a sphere of fire 100 times wider. The distance from Earth to its star is 93 million miles, a gulf so vast that light takes 8 minutes to cross it. The solar system's edge, where the Oort cloud ends, sits nearly 2 light-years away. Earth shrinks to a speck. Scale up to the Milky Way. The solar system becomes invisible. 100,000 light-years from edge to edge. The galaxy contains 400 billion star systems. If the Milky Way were the size of North America, the solar system would be smaller than a grain of sand. Earth would be invisible even under a microscope. Scale up to the local group. The Milky Way becomes one of 3 major galaxies in a volume 10 million light-years across. If the local group were shrunk to the size of North America, the Milky Way would be roughly the size of a quarter. Earth would be smaller than an atom. Scale up to the observable universe, 93 billion light-years in diameter. If you shrank Earth to the size of a virus, roughly 100 nanometers across, the observable universe would scale to approximately the size of our solar system. A virus compared to the distance from here, beyond Pluto. That represents the scale ratio between our world and everything we can detect. Another comparison makes the point differently. Count every grain of sand on every beach and in every desert across Earth's surface. The total approaches 7 quintillion grains, roughly 7 followed by 18 zeros. The observable universe contains approximately 700 sextillion stars, 100 times more stars than grains of sand on Earth. Each star potentially hosts multiple planets, multiplying the number of worlds far beyond comprehension. Time offers another lens. If you compress the universe's 13.8 billion year history into a single year, the first stars would form around January 15th. The Milky Way would assemble by early March. Our solar system would appear on September 1st. Complex life on Earth would emerge in mid-December. Dinosaurs would roam from December 26th to 30th. Modern humans would appear in the last 30 seconds before midnight on December 31st. All of human civilization, every empire, every discovery, every war, exists in the final fraction of a second before the year ends. Everything we consider ancient history happened in the blink of an eye compared to cosmic timescales. Earth itself is young compared to the universe, existing for only 1/3 of cosmic history. The atoms in your body are older than Earth. Carbon formed in stars that exploded billions of years ago. Hydrogen in your water formed minutes after the Big Bang. You are made of recycled stellar material. Atoms that once floated in interstellar clouds collapsed into earlier generations of stars, forged into heavier elements, and scattered into space when those stars died. Every breath contains atoms that were once part of distant stars. This realization shifts perspective. We are not separate from the cosmos. We are the cosmos examining itself. The universe generated stars, then planets, then chemistry complex enough to produce living things, then consciousness capable of understanding its origins. We are the mechanism by which the universe knows itself exists. Yet, despite this connection, the scale gap remains overwhelming. Earth, the Milky Way, even the local supercluster vanish when compared to the observable universe. And the observable universe itself might be a negligible fraction of the total. At each level of zoom, the previous scale becomes a point too small to see. This raises the question that has troubled philosophers since humans first looked up at stars. Why does the universe need to be so large? Light travels at 186,000 miles per second. Nothing moves faster. This speed limit, confirmed by countless experiments and woven into the structure of space-time itself, defines how quickly information can propagate through the universe. It also determines what we can observe. The universe began 13.8 billion years ago. This age is confirmed through multiple independent measurements, including the cosmic microwave background temperature, the abundance of light elements, and the expansion rate. Light has had only 13.8 billion years to travel. This sets an absolute limit on how far we can see. Even without expansion, this limit would restrict observations to a sphere 27.6 billion light-years across. But expansion stretches space, increasing distances while light travels through it. This pushes the limit outward to 46 billion light-years, the current radius of the observable universe. Beyond that distance, light has not had time to reach us no matter when it was emitted. This creates a moving boundary. Every second, light from slightly more distant regions completes its journey and reaches Earth for the first time. The observable universe grows by 3 light seconds per second, roughly 560,000 miles. Over the course of a human lifetime, the observable universe expands by billions of miles. New galaxies appear at the edge of visibility as their ancient light finally arrives. But this growth will not continue forever. The acceleration of expansion sets a maximum future observable range at roughly 62 billion light-years. Galaxies currently beyond this distance are receding too fast for their light to ever reach us. As time passes, more and more galaxies will cross this threshold and fade from view. The observable universe will eventually shrink, not grow. In 100 billion years, confirmed through projections based on current expansion rates, observers in our galaxy will see a vastly emptier sky. Most galaxies will have redshifted beyond detection. The cosmic microwave background will cool until its radiation stretches to wavelengths too long to observe. Space will appear dark and silent, except for the handful of galaxies in our local gravitationally bound group. Future civilizations arising in that era will have no way to discover the Big Bang. The evidence will have literally expanded beyond the horizon. They will measure the motions of nearby galaxies and find them gravitationally bound, showing no expansion. They might conclude the universe is static, eternal, and limited to their local cluster. All evidence of the universe's true nature will be inaccessible to them. This creates a troubling possibility. Perhaps we are already in that situation. Perhaps evidence of the universe's origins or its ultimate nature has already expanded beyond our horizon. Questions we consider fundamental might be unanswerable, not because they are too difficult, but because the relevant information has been carried away by expansion. We could be missing crucial pieces of the puzzle without knowing they exist. The cosmic horizon also limits what we can learn about the universe's geometry and topology. If space curves back on itself, but the curvature radius exceeds the observable universe, we can never detect it. If the universe has exotic topological properties, repeating patterns larger than we can see, we remain ignorant. Our sample is limited, and extrapolating beyond it requires assumptions that may prove wrong. Time also limits how far into the past we can see. The cosmic microwave background comes from 380,000 years after the Big Bang, when the universe became transparent to light. Before that moment, space was opaque, a hot plasma that absorbed photons. We cannot see earlier times with electromagnetic radiation. The first 380,000 years remain hidden behind an impenetrable veil. Gravitational waves might let us peek further back. These ripples in space-time travel unimpeded through matter and radiation. Primordial gravitational waves from the first moments after the Big Bang could still be propagating through the universe. Detecting them would open a window to epochs invisible through any other means. But the signals are extraordinarily weak, requiring detectors far more sensitive than current technology allows. Our view of the universe is fundamentally limited by time, by the speed of light, and by the acceleration of expansion. We see a finite region during a finite window of cosmic history. That sample contains 2 trillion galaxies and spans 93 billion light-years. It is immense, but it might represent only a fleeting glimpse of something vastly larger and more complex than we can currently comprehend. The question remains, if our observations are so limited, what might lie beyond? Beyond the cosmic horizon stretches space we will never observe. Light from those regions has not reached us, and, due to accelerating expansion, never will. That space could be similar to what we see, governed by the same laws, filled with galaxies arranged in the same cosmic web pattern. Or it could be utterly different. Some inflationary models predict a multiverse. During eternal inflation, quantum fluctuations cause some regions to stop inflating and form bubble universes like ours. Other regions continue inflating forever, spawning new bubbles continuously. Each bubble becomes its own universe with its own physical properties. Our observable universe is one bubble in an infinite foam. Different bubbles could have different physical constants. The strength of gravity might vary. The mass of electrons could differ. The number of spatial dimensions might not be 3. Most bubbles would be inhospitable to life, their physics failing to produce stable atoms or stars. We exist in a bubble where conditions happen to allow complexity. This scenario makes testable predictions. If our bubble collided with another in the past, the collision would leave a signature in the cosmic microwave background, a large circular anomaly. Searches for such anomalies have found nothing conclusive so far. Either collisions have not occurred, or the signatures are too subtle to detect with current instruments. Another theory suggests the universe is cyclic. It expands, then contracts, then bounces into a new expansion phase. Each cycle erases evidence of previous ones. We live in the current expansion phase, unaware of countless cycles before or after. This model eliminates the need for an initial singularity and explains why physical constants take the values they do. They evolved through cycles to produce stable universes. The cyclic model faces challenges. Entropy increases with each cycle, building up until the universe can no longer bounce. Unless some mechanism resets entropy, the cycles must have a beginning. That beginning leads back to the same questions about initial conditions that cyclic models attempt to avoid. A more radical idea proposes the universe is a hologram. All information contained within a volume of space is encoded on its boundary surface, like a hologram encoding three-dimensional images on two-dimensional film. Applied cosmologically, this means our three-dimensional universe and everything within it is a projection from information stored on a two-dimensional surface at the cosmic horizon. Evidence for this comes from black hole thermodynamics and attempts to reconcile quantum mechanics with gravity. The mathematics suggests reality has fewer fundamental dimensions than we perceive. What we experience as three spatial dimensions could be an emergent property of a lower dimensional system. Tests of this idea examine whether physical processes show signs of underlying two-dimensional structure. Results so far are ambiguous. All these theories remain speculative. We can only observe our local cosmic neighborhood. Extrapolating beyond requires assumptions we cannot verify. The universe might be one bubble in an eternal multiverse, or it might be everything that exists. It might be cyclic, holographic, or something we have not yet imagined. Current observations cannot distinguish between these possibilities. What we do know is that the observable universe contains 2 trillion galaxies, each with billions of stars, arranged in a cosmic web stretching 93 billion light-years. That structure formed from tiny density fluctuations in the early universe, amplified by gravity over 13.8 billion years. Dark matter provides the scaffolding. Dark energy accelerates the expansion. Ordinary matter forms galaxies, stars, planets, and eventually life. The Milky Way sits in this vast cosmos as one galaxy among trillions. Our position is not central or special. We orbit an average star in an average location within an average galaxy. Yet from this average location, we have mapped the structure of the observable universe. We have traced our cosmic address from Earth to solar system, to galaxy, to local group, to Virgo supercluster, to Laniakea. We understand the hierarchy. And we have realized that hierarchy might extend forever in both directions. Smaller structures within atoms, particles, forces we have not yet detected. Larger structures beyond the horizon, patterns we cannot observe, scales that make superclusters look like atoms. The universe might be fractally infinite, with no smallest or largest scale, only levels we can currently access. But regardless of what lies beyond observation, we can grasp one profound truth about our position in the cosmos. The Milky Way measures 100,000 light-years across. The observable universe spans 93 billion light-years. The actual universe might be infinite. These numbers define our place in the cosmic hierarchy, and that place is humbling. We live on a planet 8,000 miles wide, orbiting a star that is one among 400 billion in our galaxy. That galaxy is one among 2 trillion in the observable universe. The observable universe might be a tiny fraction of the whole. At each level, the significance of the previous level diminishes toward zero. Yet here is the paradox. Despite occupying such an infinitesimal position, we understand the structure surrounding us. Humans, confined to one planet, have mapped the cosmic web. We have measured distances to galaxies billions of light-years away. We have traced the history of the universe back to moments after its beginning. We have glimpsed the underlying architecture of reality. This represents an achievement almost as improbable as our existence. The universe has no obligation to be comprehensible. Physical laws could have been random, chaotic, impossible to decode. Instead, they follow mathematical patterns we can discover. Nature is not deliberately obscure. It answers questions for those who learn to ask properly. Our comprehension comes from light. Photons travel across cosmic distances, carrying information about their sources. By collecting and analyzing these photons, we reconstruct the universe's contents, distances, and evolution. Light takes billions of years to reach us, but when it arrives, it tells stories about galaxies, stars, and the spaces between. We are archaeologists excavating the past through astronomy. The scale gap between Earth and the observable universe mirrors the scale gap between atoms and humans. An atom compared to a human is similar to a human compared to the Milky Way. We exist at intermediate scales, neither smallest nor largest, able to perceive both directions. This middle position allows perspective. We are small enough to be humbled, large enough to understand. Knowing our cosmic address changes nothing about daily life. Gravity still pulls, light still travels. The laws of physics that govern galaxies are the same laws that govern falling objects on Earth. The universe operates consistently across all scales we can measure. This consistency suggests the laws we discover are not merely local accidents, but fundamental properties of reality. It also suggests we are not alone. 2 trillion galaxies, each containing billions of stars, implies trillions of planets exist in potentially habitable zones around their stars. The chemistry of life uses common elements formed in stars throughout the universe. The same physical processes that led to life on Earth should occur elsewhere. Whether that life develops intelligence is unknown, but the raw numbers suggest billions of opportunities. If other intelligences exist, they see the same universe we do from their own vantage points. They observe galaxies receding, measure the same cosmic expansion rate, discover the same dark matter and dark energy. The universe does not hide its nature. Any civilization that looks carefully will uncover similar truths. We might be isolated by distance, but we are connected by shared discovery. Our place in forever is this. We exist briefly on one world in one galaxy, in one supercluster, in an observable bubble that represents a tiny fraction of a possibly infinite cosmos. We are temporary concentrations of matter that have become aware of themselves. The atoms in our bodies formed in stellar furnaces and will return to space when we die. We are the universe experiencing itself, comprehending itself, measuring itself. That we can understand even a fraction of the cosmic structure surrounding us is remarkable. That we evolved the capacity to ask these questions is statistically improbable. That the universe allows us to answer them suggests something profound about the relationship between consciousness and reality. The Milky Way is vast beyond intuition. The observable universe is vaster beyond comprehension. What lies beyond might be infinite, and somewhere within that immensity, on a small, rocky world, beings evolved who can grasp the scale of their cosmic neighborhood. That grasp does not change the scale. It does not make us larger or more significant, but it means the universe is not just physical, it contains meaning, and that meaning exists because we are here to recognize it. We are infinitesimal, we are temporary, we are insignificant by any measure of size or duration, and yet we have mapped the structures within which we are embedded. We know our address. We understand our place, and that understanding, fragile and incomplete as it might be, represents consciousness reaching across cosmic scales to glimpse the architecture of everything. The observable universe contains 2 trillion galaxies spanning 93 billion light-years. The Milky Way is one of those galaxies. Earth is one planet in that galaxy. You exist on that planet for a brief moment of cosmic time. And during that moment, you can look up, see light that has traveled for billions of years, and comprehend the journey it took to reach your eyes. That is your place in forever.